welcome to our second seminar series. So last time we had two excellent talks on wireless communications, and today we have another two excellent researchers working in the area of multimedia signal processing, and especially on the interaction with this extended reality. So the two speakers we have today, one is Professor Min-Chun. She's a professor in the Department of Computer Science at National Tsinghua University, and the other is Professor Min-Chun from National Taipei
University of
Technology. Yeah. So I think they also work closely together on a lot of sports training related research, and which is a really exciting field that's emerging in recent years. Okay. So I think, without further ado, let's welcome our first speaker, Professor Min-Chun.
Okay, hello everyone. Now I'm a professor in the Department of Computer Science in National Tsinghua University, but actually I have been involved in National Yangming Jiaotong University and the National Taiwan University, and also National Chengong University. So actually, I'm a person who like to explore a lot of things. Yeah, and also my research also include a lot of things, including multimedia content understanding, and multimedia retrieval and recommendation, multimedia content creation and authoring, and also human-computer interaction, computer graphics, AR, VR, and some mobile application, and its design of cloud computing. So for example, recently we have some research project about how to model the 3D things. So we have a lot of work on using AI models to reconstruct the 3D thing, or we call it Tsing understanding. And based on the understanding of the Tsing, and we can apply the representative features to explore or navigate in a mapless space. And we also did a lot of projects related to sports video analysis. For example, we can extract highlight real-time and automatically. And also we can analyze the shooting of the players, including the statistic of their hotspots or their tactic. And also we try to analyze the 3D information of player or the objects in the sports video. We also try to see what the VR technology can achieve. For example, we can use VR technology to develop some system for sports training, and also we investigate whether AI technology can be included in the content creation work in the VR. And in addition, we actually investigate the other kind of senses rather than just visual or audio sensing. Okay, so we investigate the haptic feedback in VR and also some olfactory feedback in VR. And today, what I would like to introduce more is about the emotion analysis in multimedia and VR. So today we will include three small projects. The first one is how to construct the common representation space for emotion between the music and the video data modality. And the second one is how to analyze the affective states of VR users when they are watching the video displayed in different formats in VR. And the third one is the one that I think more interesting. We try to investigate how to encourage the user to label their affective states in the VR. Okay. So the first one is how to correlate the music and the video based on emotion. Let's first think the problem, how to choose a suitable background music for a video. For example, we have a video like this. So how do you feel? Horrible, right? Yeah, so if we remove the music background music, so there's no background music, and let's watch the video again. Any difference? Not so horrible, right? And how about this one? Not horrible, and somehow it's a little bit funny, right? So actually, different background music can bring different emotion to the user. Okay. So we believe that actually there are strong connections and correlations between music and the video, which we call then different data modalities. Okay, and we try to. We believe that this kind of strong connection actually are correlated to emotions that the content can bring to the user or the audience. And in the fields of psychology, actually the researchers, they try to classify human emotions based on different models. For example, we can classify emotion to 6 categories like anger, disgust, fear, happiness, sadness, or surprise. Or we can divide them into more fine-grained categories like the aprimary bipolar emotion or the circumplex models. However, these kind of emotion models, they are difficult to model different level of angers or specific emotions. So in our work, we actually use different kind of emotion model. This emotion model is called valence and arousal model, which means we decompose the concept of emotion into 2 dimensions. The first dimension is about whether the emotion is more positive or more negative. And the other one is whether the emotion is more excited or more calm. Okay, so in the later work, we actually try to investigate the emotion based on the valence arousal model. So the label of the emotion of the content is actually a value. Maybe it's a discrete value from 1 to 9, or it's a continuous value from -1 to 1. Okay. So every content may have some kind of emotion, and this emotion have some label, and this label is represented by a 2-dimensional data vector. And our goal is to can be actually decomposed to 3 subproblems. The first problem is how to extract the emotional feature in the music. So we can actually design an AI encoder to extract the features to represent the emotion of the music. And similarly, we can design another AI encoder to extract the the video features to represent the emotion in the video. And the third subproblem is how to correlate the emotional feature in different data modality. Okay. So we try to find the common embedding space, which means that based on the extractive feature in the music data and the video data, we will reproject them into a common space. And if they contain the same emotion concept, then in the common space, the 2 data should be very close. Otherwise, they should be separate apart. Okay. So our model have 3 parts. The first part is a music emotion pre-trained model, and the second part is a video emotion pre-trained model, and then the third part is how to correlate the 2 modalities. So here, actually, there have been a lot of work focusing on how to design a feature extractor to analyze or classify the music emotions. So here I will skip the details, but you can imagine that there is a convolutional neural network, and based on this convolutional neural network, actually you can use 1 layer as the emotional feature. Okay, so for example, in this case, we use this layer as the emotional feature for music. And similarly, for video, we can also design another convolutional neural networks and also choose 1 layer of it to be the high-level representation for video emotion. And based on the two high-level features, we try to ignore the feature illustrator for music and the video. We directly use their embedding because we already has the pre-trained model to illustrate the corresponding feature. So every input data can be passed through the encoders and resulting in the corresponding embedding features. And based on the two features, we try to reconstruct the correlation between music and video. So for example, in this structure, we have an encoder to further project the music embedding into a common space embedding, and so as for the video one. And our idea is that in the common embedding space, these two should be very correlated. So we need an emotion classifier to constrain this kind of embedding that can actually represent the concept of emotion. And also we design another two decoder for the music and the video correspondingly. These two decoders is trying to reconstruct the original embedding for music and the video, which means this common embedding not just can be used for emotion classification, they can also have the ability to be reconstructed back to the original embedding. Okay? And furthermore, we decide three discriminator which can be classified whether the input is a real is the embedding from a real music, or actually it's a embedding from a generated music. Similarly, we have another discriminator to classify whether it's a video embedding directly illustrated from the video, or it's a generated embedding. And in addition, we have another two discriminator which try to classify whether the embeddings are from the music or from the video, or whether they are from the common embedding or the original embedding. Okay, so this kind of design is somehow very complex. But based on the complex design, we can actually constrain the common space to be more representative. Okay. So here I will, due to the time limitation, I will skip the details of how we design the loss functions, but I list all the loss function we design here for your reference. So here for the discriminator, we can design the adversary loss for both the music and the video part. And also we use the reconstruction loss, the distance loss, the classification loss, and the correlation loss to constrain the O decoder and the encoder. Okay. So I will skip all the mathematical parts and directly jump to the data set we use to evaluate the proposed model. Actually, it's difficult to find a proper data set to evaluate our work. So our idea is that maybe we can use some benchmark in the movie fields. For example, the movie, they already have the music, the background music made by the very professional experts, right? So we can use the movie as our benchmark. So here we use the PM-EMO expansion data sets, and in these data sets, actually they have more than 500 paired data. So which means every data has the video content and the background music. So we can we can assume that the given data already has been a very good correlation between the music and the video. And we try to evaluate whether our common embedding is good based on the correlation of the illustrated common embeddings. And the correlation can be defined based on the two distance. Okay. And here you can see that based on our model, we can achieve quite good results compared to the state-of-the-art works. And also we try to do some ablation study because we have a very complex network. So each component we need to prove whether it actually has some achievements. Okay, so here you see that every component in the pre-mentioned framework is actually very important. And based on the common embedding, we can use them to retrieve data. For example, if we already have a music, then we can use our network to extract the common embedding for the music and find which video is suitable to be matched with the music and vice versa. Okay, so here we also evaluate if we use our model to extract the common embedding, then can our model have good performance in the cross-modality retrieval problem. So here you can see that our result is also very good compared to the other framework. And we also visualize the common embedding space. So as you can see, based on our proposed model, the data, the music or the video with very close emotion, they are actually very close in the common embedding space. Okay. However, for emotion, it's very correlated to what the user really feels. So we need to do user study. So we also designed a series of user study which contains 4 stages to investigate whether our model has a very good pre-trained model to extract the common embedding, or whether our model has very good results in pairing all the data. Okay. So the process of the user study is somehow like that. We will have a random pair of our result or a ground truth data, and then we will ask the user which one is better. So sometimes they will choose the one with ground truth. However, our model also have good performance, so sometimes they will also choose our proposed model can result in the better pairing results. Okay. And because if we have time, then later we can go back to the user study. Okay. Okay, that's a lot of cases. So later, if you are interested in our user study, we can go back. And the second work is about the affective state of VR HMD user when they are watching videos displayed in different formats. For example, we already mentioned that we can use the emotion model to label the emotion of the data. Okay, for example, given a video content like this, then we can display the video content in VR space and let the user to label their current emotion based on the 2-dimensional space. Okay. And in the past, actually, there have been a lot of research focused on the design of how to ask the user to label the data for you very efficiently. So for example, some propose that we can design an interface like this. It's a grid tool, grid-based tool. So when the user see the content, it can use the keyboard or mouse, or in the VR, maybe the controller, to label their corresponding emotions. Or some is use the emoji as the representation and help the user to more clearly understand which kind of category or position they need to label for the emotion. However, in our work, we try to investigate in the VR space. We can actually let the user watch a 2D video in the VR, or watch the panorama in VR, or watch the 360 videos in VR, actually the feeling is quite different, okay? So this is how we convert the original data into different kind of formats. And we also ask the user to label the emotion based on the controller. So let's see what's the difference. Let's see the video directly. Okay. So this video shows that, this is the 2D version, 2D format when the user see in the VR head-mount display. And at the same time, they will label the corresponding affective state. Okay, so when they are watching the video, they can actually continuously label their affective states, even they are watching the same content. Okay, because the video may contain different emotion along the time. Okay. And this is the panorama format and also the 360 format. So you can observe the difference between different formats. And at the same time, we also record the some emotional signals. For example, we record the GSR signal, PPG signal, and the IMU signal, and also the attention relaxation, and some EEG signals. Okay, and also we record their eye gaze information. And we design this kind of interface. So when they are watching the content, we actually can monitor their affective states based on different kind of sensors. Okay, and right now we already collect a lot of emotional data. So if you are interested in affective states researches, maybe you can reach us and we can release the data to you. And here is the comparison about what's the difference between our proposed data set and the existing ones. You can see that actually our data sets are more comprehensive because we not just include the label of emotion, we also have more objective evaluation based on different sensors signals. Okay. And this is how we collect the data sets. So I will skip this part. And then we try to analyze the result to observe what's the difference when they are watching the video, the same video, but with different data formats. And we observe that actually when the participants are watching the 360 videos, they are trying to explore the environment. So the label of their affective states is actually unreliable because they pay attention to explore the world instead of feeling the world. Okay, so their affective states is not so obvious. Okay. So it's actually encouraged us to do the following research based on, if you try to investigate the affective state of VR user, actually maybe you can use the 2D format or the panorama format instead of the 360 video data formats. Okay. And the last one is the gain-actuated mutuality, our work for evoking affective states. And this work is because that when we trying to do the previous work, the user come to our lab and they just sit there and try to label a lot of data and they feel very boring. So unless you have a lot of money to encourage them to label for you, otherwise it's very difficult to collect this kind of a large amount of data sets. So our idea is maybe we can make the labeling process as a game. Okay? So this is a concept. It's an interaction game. So this is the labeler. the VR labeler. So he or she will still try to label their affective states or emotion in the VR space. So they will watch the video, which is also displayed outside. Okay? But what video they are watching is actually selected, not randomly selected by the system, but it's randomly selected by the system and also suggested by the other player. So the other player here, she is playing a dart game. So he will throw a dart, and if the dart stops in this position, then we will find a we will find a data which is more close to this position and show this data in the VR display. Okay? And which means what the user watch is actually determined somehow by the other player. And the other player doesn't know he is affecting the results seen by the other VR experiencer because she thinks she's playing the dart game. So she can also label the data, but with some randomized mechanism because you are not very good. If you are not very good at throw the dart, then you think, oh, the label should be here, but there is a little bit, there is some probability that the result is not the one you expected. Okay? So our data set will collect it based on the label of the VR experience. But for this one, she is actually playing the dart, but doesn't affect the labeling result. She or he only affect what the VR user sees. Okay, and in the VR space, actually all the affective states will be visualized like this. Let's directly watch the demo video. This is what the VR experiencer sees in the head-mount display. And this is what the other player sees on the wall. Okay. Okay, we directly. And all the, for example, EEG signals or the eye-gazing data, they are visualized in a more like artwork. Okay. So this is the result. We call the project a stimulus loop because the two players, they are like a loop. Each the VR experience. Okay, let's see.
Large-scale media data has changed the way users receive.
What the VR experiencer sees is actually affected by the other player, and what the player sees is actually affected by the VR experiencer because all the labeled affected states and the response affected signals will be displayed outside too.
Stimulus loop involves two participants, one serving as the VR experiencer and the other serving.
So he's labeling his affected states, and all the EEG signals or eye-gazing signals will be displayed outside. So the other player can see the affected state of the VR experiencer, and he can decide whether he wants to change the player's affected state by throwing a dart to another emotion.
The player could observe the feedback of the VR experiencer to throw the next dart, and continually evokes the VR experiencer's.
And this one is more like an exhibition research. So we show the demo in the ACM Multimedia conference, and we try to see when every user comes to our booth, we try to record all their affected states and see what happens to our final data set. So we will record all the signals and try to visualize the results of the signals. And every day we can observe different things.
Which shows affective states in two-dimensional coordinates of valence and arousal. The reticle emphasizes that the VR experiencer is tracked as a target under surveillance. Here to presents the visualization of user behavior. The first and third quadrants indicate the information of relaxation and attention, and the second.
Okay. So based on the three sub-work, actually our future work is this project, emotion-aware piano performance with AI-generated visual content. So in this project, we cooperate with a piano performer who is very famous in the international piano field. And we try to analyze the music signal, not just for the emotion of the player, but also the emotion in the original music content. And based on the emotion information, we can take the emotion concept as the condition to generate the visual content in the concerts. Because I think most of you has the experience of attending a piano concert, right? Have you ever fallen asleep? Yeah, so it's because we only listen to the music, but we don't understand what happens, what's the meaning of the music. So if we can have some visual content to tell us the story or the background story of the music, then maybe the concert will be more interesting. So that's the idea of that's the motivation of this research project. So we try to understand the emotion of the content, and also we try to understand the semantic meaning of the original music, and based on the semantic meaning, we can use generative AI models to generate the final video. Okay, so this generative video can cooperate it with the concert. Okay, that's all my presentation. Thank you.
No Q&A. Please take some questions.
Oh, okay.
Do we have any questions?
中文应该也可以。
对，中文也可以。
谢谢。
Can you explain what is emotion in your project? Emotion means.
For example, you feel horrible or angry or excited or happy. Yeah, so as I mentioned earlier, there are different kind of emotion model, right? So in our work, we do not directly classify them into specific class, but we believe that every emotion can be decomposed to two dimensions. One is how intense the emotion is, and the other is the emotion is more positive or negative. Like happy is more positive, angry is more negative, like this. So you can use continuous values to describe one emotion of human. Yeah. Okay.
Any other questions? I have a couple of questions. So in your last work, is there any reward mechanism to sort of motivate the users to continue playing?
Yeah, it's actually, we are trying different kind of games in the player part. Yeah, so for example, this one I showed that we ask the user to play the throw the dart game. So he will get some reward if, for example, the labeler, he has labels two-dimensional data on the screen. So if he or she try to throw the dart on that position, he will get some score. However, he will also get a little bit score if he try to choose another kind of emotion data, because we encourage the user to label different kind of emotion data. Yeah, so it's actually very difficult. We are still designing the mechanism. It's very difficult to design the game simultaneously encourage the player to play the game and encourage the labeler to keep labeling the different kind of videos. Yeah.
I also have a question about the first work. In the first work, you're trying to match the different music segments in the video clips, right? Hoping that they have the same
similar emotion. Yeah.
Yeah, but what if is there an application where people want to make different combinations for a different overall effect? Like you showed at the beginning, if you assign a sort of kind of a horror movie feel to the music, then it appears horrible. But then if you want to
Make it funny.
combine it, make it funny, then you might not want to choose some music that's horrible.
Yeah, I think that's actually the motivation why we do it. We have conducted this research because we want to develop a tool for maybe the movie maker to decide what kind of music background they want to choose. So we have a list of recommended music which is based on the emotion. So he can choose, and also he can choose, I want some kind of emotion which, for example, we can also provide an interface like the two-dimensional interface, and he can choose, I want this kind of emotion. Then could you recommend the corresponding music with this kind of emotion? Yeah.
Okay. Thank you. So do we have any other questions? So if not, let's thank Professor Wu again.
Thank you.
Thank you. So,